Hello, welcome to a differential equations show, season or chapter 2.6. Okay, we're going to talk about substitutions and transformations. Okay, so let me just go ahead and tell you what the transformations are in this video, and then in the next video we'll do examples, okay, in the next videos. So the first type of equation is what we call homogeneous equations. I'm a little conflicted with this word homogeneous or homogeneous, not just on how to pronounce it, but also in that we use it for more than one thing, even particularly in a differential equations class, okay? So right now, what it means in this setting is that if we have dy dx equals f of xy, okay, and we know that we can write f of xy as some function of y over x, okay? Then we're going to take u, which we assume to be also a function of x, is that y over x. Okay, and we'll make a transformation. So let me explain what the transformation is real quick. So the transformation is I'm going to write xu equals y. Okay, and then taking the derivative with respect to x on both sides, we're going to get x du dx plus u equals dy dx. Okay, so we're going to run our homogeneous equations through this transformation. Okay, so u of x is y over x, and dy dx is going to be x du dx plus u. And this should give us something new to work with, which may be solvable now. Okay, the hope is that it would be solvable. Okay, that's the first type of equation we're going to see. Second type of equation we're going to see is, I don't think it has a name other than dy dx equals g of ax plus by. Okay, that's just what it's called in the book, so we'll keep it that way. We'll make the substitution. U equals ax plus by. Okay, and now du dx is going to be a plus b dy dx. Okay, so if we want to write this in terms of dy dx, dy dx equals, I'm just going to write it 1 over b du dx minus a. All right, so that'll be the transformation that we're dealing with. So u is ax plus by, and dy dx. Now, I'm writing these down, but I don't really think it's worthwhile memorizing. You'll know what the substitution is, and based on the substitution, you can easily find what the new derivative is. Okay, it shouldn't be too crazy difficult. Okay, next type of equation we're going to deal with are called Bernoulli equations. Okay, Bernoulli equations are of the form dy dx plus p of xy equals q of x y to the r. Okay, now here the substitution is not as natural. Okay, the substitution is going to be, we're going to take v equals y to the 1 minus r. Okay, and then I won't do the dy dx. We'll do that just as we go along. Okay, so let me just write that substitution down. Okay. And finally, the last type of equation that's presented in the section are called linear coefficients. Okay, and so this is a function where we have a1x plus plus b1x, b1y plus c dx plus a2x plus b2y plus, let's call it d dy equals 0. And what we want to do is we want to find h and k, okay, so that we write it at lots of different ways. I'm going to write it as u equaling x minus h, v equals y minus k. And the reason I'm going to write it that way is so that u plus h equals x, and v plus k equals y. And we want to find that so that a1x plus b2y plus c equals a1u plus b2v, and sorry, that should be one there. Oh, and a2x plus b2y plus d should equal a2u plus b2v. Okay, now what does that give us? What does that give us? Why would we do that? Why? Okay, we do that because if we have a1u plus b1v, now dx is going to become du plus a2u plus b2v dv. Okay, so if we do that, let's solve this. We can actually make this into a homogeneous equation. dv du is going to be negative a2u plus b2v over a1u plus b1v, and then we can factor out a u to get negative a2 plus b2 v over u, a1 plus b1 v over u, and now this equation is homogeneous. Okay, and by homogeneous, I mean this type of homogeneous. Okay, all right, so let's take a commercial break, and I'll be back with some examples.